Alrighty, so we're going to look at a revision exercise looking at uniform gravitational fields before we start on radial fields in class. So let's have a look at some of the problems that I set. Okay, so zoom out here a little bit. So we've got a 0.20 kilogram arrow fired from ground level at an angle of 30 degrees at a speed of 15 meters per second. Calculate the time taken to return to ground level. So essentially, if we think, let's draw a diagram over here on the right hand side where we've got space. So if you think this is your ground, essentially what's going to happen is it would take this kind of path here, and its initial velocity is 15 at an angle of 30 degrees. So the first key thing to remember is that the time an object is airborne is dependent on the vertical component of velocity. Horizontal has nothing to do with it, that just dictates how far it goes. So let's first of all calculate that. So we want the vertical component of velocity, which will be 15 sine 30. So sine 30 is a half, so it's 7.5 meters per second. That's the vertical component of velocity. So we want the time it returns back to ground. So let's use this SUVAT equation here, like this. So when it returns to ground, S is going to be 0. You can see this is actually a quadratic equation, and quadratic equations have two solutions. So one solution to this equation when S equals 0 is T equals 0, because it starts at ground level. But the other solution will be this point here when it returns to the ground. So we want to, let's do some cancelling out. So we know that S is 0 when it returns to the ground. We know that VV is this U value, and we know that the A is going to be minus G, because it's acting against the vertical velocity. So let's put that all together. So we know that T 7.5 minus 9.81 T over 2 is equal to 0. So we know one solution is T equals 0, but we don't really want that solution, so let's get rid of that. And then from this, so this expression, the brackets would need to be 0. So essentially T is going to be 7.5 times by 2 divided by 9.81, and when we calculate that, we're going to get a value of 1.5 seconds as the flight time of the arrow there. You can do this using V equals U plus AT and working out the time to reach the peak up here when the vertical velocity would be 0, and then double that and you should get the same time, but I think this is the easiest way to go about doing it. And last thing, so it wants the horizontal distance, so it wants horizontal distance. So the acceleration in the horizontal direction is 0 because gravity acts vertically, so we can just use this simple expression. So it's going to be 15 cosine of 30, because that's the horizontal component of velocity, times by 1.5 in the unrounded form, which gives us a 20 meter horizontal displacement there. So those are the first two parts. So then let's look at the next part. So describe the speed of the arrow when it turns to the ground, explaining your answer using the concept of conservation of energy. So let's rule this off so we're not getting mixed up between stuff. So first, if there's negligible air resistance. So if you think what happens to the arrow, it has kinetic energy initially. It's transferred to GP at the top of it, and then it would be transferred back into kinetic energy. So if there is no work done against air resistance, these two values, the kinetic energies, should be the same as each other. Therefore, so the velocity is going to be the same, i.e. 15 meters per second. So the way to explain that is to go, well, this is your conservation of energy expression here, where there's no work done term because there's no force of friction or air resistance taken into account. Therefore, initial kinetic energy equals final, so the velocity must be the same, so it's going to be 15 meters per second, because that was the initial velocity. Okay, so thinking about this expression in terms of air resistance, so how it would change, so we still got the initial kinetic energy, so we would transfer it into GP plus some into work done against air resistance, which would then get transferred into final kinetic energy and some more work done against air resistance. So we can see that this term here is essentially causing energy to be transferred out of the arrow into heat energy in the surroundings. So actually we can see that the kinetic energy of final is going to be smaller. So the velocity therefore would be smaller than 15. So that's how you describe its velocity, and the explanation is that some energy is going to be transferred to the surroundings, reducing the total energy available to be kinetic energy. Okay, so let's move on to a more complicated example. Alright, so in this next question, instead of just firing from the ground, we're going to fire from a 20-meter high tower. We want to find the new horizontal distance travelled and the final velocity of the arrow when it strikes the ground. So in terms of what this looks like, the arrow is now fired from up here, still going to engage in projectile motion like this, but we start from a height of 20 meters like this, and you still have like a velocity of 15, and it's still at 30 degrees like this. So the final velocity we're going to actually do using conservation of energy. So applying conservation of energy, or CO for short, initial kinetic energy plus the initial gravitational potential energy is going to be equal to the final kinetic energy. So what we're going to do is use the ground as a 0 joule line, and then obviously at 20 meters it's got gravitational potential energy of mg20 joules there. So our 0 line is going to be the ground, which means that half mvf squared is going to be equal to half mvi squared plus mghi. So we can already see we can get rid of the m's. I'm going to multiply through by 2 as well. So we can get the final velocity is going to be the square root of 2 times 15, sorry, not 2 times, because we've multiplied through by 2.5, so it should be 15 squared plus 2 times 9.81 times 20, and when we do that we will get a value of 25 meters per second, so we've increased the velocity, which is what you'd expect because you've transferred in some energy. So it wants to calculate the new horizontal distance travelled by the arrow. So let's set this problem up the same way we did previously, using our s equals ut minus half at squared equation. So that's what we're going to do. Remember, u was 7.5, and we know that a is minus 9.81. Set. What's the displacement is now going to be minus 20, because it's 20 below the original position. So let's put in the values there. I would normally encourage you to rearrange in algebraic form, but in instances of SUVAT equations, since a lot of things end up being 0, it's usually more effective here, and we end up with a quadratic equation. So we know that, so 9.81 over 2 t squared minus 7.5 t minus 20 is equal to 0. So we can solve that using the quadratic formula. But let's multiply through by 2 first of all to get a nicer expression. So multiply by 2, so 9.81 t squared minus 15t minus 40 is equal to 0. So remember, our quadratic formula is minus b plus or minus square root of b squared minus 4ac all over 2a. So that's going to be 15, because it's minus 15 but minus b, plus or minus square root of 15 squared minus 4 times 9.81, because that's what multiplies by t squared, times minus 40 all over 2 times 9.81. Now one of those solutions gives you a complete nonsense answer there, which makes no sense, but the sensible answer you can get out of this is t is 2.9236, blah, 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 blah. So the horizontal is going to be, again, u times t, so it was 15 cosine 30 times 2.92, blah, blah, blah. And when we calculate that, you end up with 38 meters. So we can see we've managed to increase the range by going to the top of a tower. We've gone from 20 to 38 meters, and we've managed to increase the velocity to 25 from 15. So very advantageous. Definitely climb on top of the wall if you're trying to shoot people with arrows there. Okay, good. Now we've established that. Let's move on to the next level, which is a very tasty question with some air resistance. All right, so we've got the same scenario as we had before. So let's just remind ourselves, we've got the ground level, we've got it fired from up here, so it's going to go like this. We're 20 meters above. But the difference here is we've now got air resistance, which acts in both the horizontal and the vertical directions. So the problem we're going to have here is when the object is traveling upwards, so when the velocity is upwards, if we think about acting on it, we've got the acceleration due to gravity, and we'll also have the acceleration due to like your friction there. But when the object is coming back down again, we've still got acceleration due to gravity, but actually during this phase we've got the acceleration due to friction acting in the opposite direction. So let's work out what the net I'm going to call this AU, so the acceleration upwards, they're going to add together, so it'll be 9.81 plus we've got 0.20 is the force, so mass was 0.20, so we're going to get 1, so that's going to be 10.81 meters per second squared, and the acceleration during the downward phase, let's remember that these should all be negative because they're all against the motion, actually. And when it's in the downward phase, the acceleration is going to be 9.81. It's plus because it's in the direction of motion this time, but we're going to subtract the value of 1, and you get 8.81 meters per second squared there as the acceleration, and in this case that's a plus because it's working in the direction of the motion there. Okay, so we can essentially what we're going to need to do is work out the time taken to get up here to the top and the time to hit the ground, and then we'll add those times together to give us the total time. Okay, so the time upwards, we're going to get by doing v minus u over a. So when it reaches the top, v is going to be 0, so it's just going to be minus 7.5 divided by minus 10.81, which is going to give us a total value, if we plug that in, of 0.69382, blah blah blah. The time downwards, we can't use that same equation anymore because we don't know what the final velocity is. So let's we're going to use our old friend s equals ut plus half a t squared again. So we know s is going to be minus 20 again. We know that u is 0, and then we know it's going to be half times 8.81 t squared. Where we rearrange and solve that, we get a value of t of 2.13097, la 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 la. So we know the total time is going to be 2.8245, blah blah blah, by adding those two times together. So our horizontal distance is going to be, we can't get rid of the half at squared this time because we've got an acceleration now acting in the horizontal direction of air resistance. So that's going to be 7.5 times the value of t minus half. Acceleration is 1 because it's 0.2 divided by 0.2, and then let's put our t squared term in there, and we calculate that, we get a distance of 33 meters. So you can see that due to air resistance, it's gone from 38 to 33 meters, so it's been shortened, as you might expect. In terms of the vertical velocity, we can work out what that would be. So we're going to use v equals u plus at. So when it's at the top of its motion, its vertical velocity is 0, so we can get rid of that. So that the final component in the vertical direction of the velocity is just going to be 8.81 times by the time it takes to go downwards, which we had as 2.13. So it's going to give you a value of 18.77232. And the key thing is you have to put the downwards time in here because we started from the top. And the horizontal, we can, so it started off in the horizontal direction at 15 cosine 30, and it had an acceleration of 1 acting on it the whole time. So this is just going to be t, and we get a component there of 10.165. So these were speeds. And we put those two together by using Pythagoras, and that's going to give us a velocity of 21 meters per second. So again, we've reduced our final velocity, as you might expect once you factor in air resistance there. So just to recap what we've done here, so we started from the top of the motion in this expression, so that's why u was 0, and during the downwards it had this acceleration for this time. Then for the horizontal, this is the initial horizontal velocity, had an acceleration of 1 for the total time now, because that's acting the whole time, so that gives us this, and we use Pythagoras with these two numbers to give us this one here to finish. So the last question asked, calculate the work done against air resistance during the flight. So let's think about the conservation of energy equation. So initially it had some kinetic energy and GPE, and then finally it would just have some kinetic energy and some work done against friction. So the work done against friction, it's going to be, we can take these terms out. It's going to be VI squared minus VF squared plus 2G, the initial height there. So if we plug our initial velocity, our final velocity, and our initial height of 20 in there, and the mass of 0.2, we end up with a value of 16 joules there. And that's how we essentially solve this question, and that completes this problem set.